Welcome to this video on atoms and radioactivity. We will cover the structure of an atom, atomic and mass numbers, isotopes, ionizing radiation, and nuclear equations. An atom has a small central nucleus made of protons and neutrons, surrounded by electrons. A neutral atom always has the same number of electrons as protons. The atomic number is the number of protons. The mass number, or nucleon number, is the total number of protons plus neutrons in the nucleus. Protons and neutrons have a relative mass of 1, while electrons are much smaller. Protons have a relative electric charge of +1, neutrons have 0, and electrons have -1. Nuclear notation uses the mass number and the atomic number with the chemical symbol. For carbon-14, 14 is the mass number, and 6 is the atomic number. Isotopes are atoms of the same element with the same number of protons, but different numbers of neutrons. Hydrogen has 3 isotopes: hydrogen-1, deuterium, and tritium. For uranium with 92 protons and 143 neutrons, the mass number is 235. The two notations are uranium-235, or the nuclear symbol with 235 on top and 92 on the bottom. For nitrogen-13, there are 7 protons and 6 neutrons. Cobalt-60 has 27 protons and 33 neutrons. Gold-197 has 79 protons and 118 neutrons. Plutonium-239 has 94 protons and 145 neutrons. Ionization occurs when an atom gains or loses electrons. Losing electrons results in a positive ion. Gaining electrons results in a negative ion. Radioactivity is the random decay of unstable nuclei, emitting ionizing radiation. Henri Becquerel discovered radioactivity in 1896. Alpha particles are 2 protons and 2 neutrons, strongly ionizing. Beta particles are high-speed electrons, moderately ionizing. Gamma rays are electromagnetic waves and are weakly ionizing. Alpha particles are stopped by paper or a few cm of air. Beta particles are stopped by 1 centimeter of aluminium. Gamma rays require several cm of lead or 1 meter of concrete to stop. Alpha and beta particles are deflected in opposite directions by magnetic fields due to opposite charges. Alpha particles are deflected less than beta particles due to their larger mass. Gamma rays are not deflected as they are uncharged. The same deflection patterns occur in electric fields. Alpha and beta particles deflect in opposite directions, with alpha being deflected less. Gamma rays remain undeflected. Let's test your knowledge of atoms and radiation properties. Atoms consist of a very small nucleus, containing protons and neutrons surrounded by electrons. Isotopes are different atoms of the same element with different numbers of neutrons. The atoms of some substances are unstable and radioactive. They may give off alpha or beta particles or gamma rays. Gamma rays are the most penetrating type of radiation. Alpha is the least. Alpha decay occurs when an unstable nucleus emits an alpha particle, which consists of 2 protons plus 2 neutrons. This process is commonly seen in isotopes of the heaviest elements. For example, the decay of uranium-238 to thorium-234 plus an alpha particle. Remember that both the mass and atomic numbers must balance on each side of the equation. Here is an example equation for plutonium-239 decaying by alpha emission to uranium. The sum of the mass and atomic numbers on the reactant side equals the sum on the product side. Beta particles are high-speed electrons emitted by isotopes with an excess of neutrons. A neutron decays into a proton and an electron. The proton stays in the nucleus, but the electron is emitted as a beta particle. In the decay of carbon-14 to nitrogen-14, a beta particle is emitted. The beta particle has an effective atomic number of -1, balancing the atomic numbers on both sides. Let's try to write the equation for sodium-25 decaying by beta emission to magnesium. Sodium-25 decays into magnesium-25 and a beta particle, where the atomic number increases by 1 and the mass number remains unchanged. Gamma decay is the emission of electromagnetic radiation from an unstable nucleus, often following alpha or beta decay as the nucleus loses excess energy. For instance, cobalt-60 decaying to cobalt-60 plus gamma radiation. Both alpha and beta decay cause an element to change its atomic number. Alpha decay also changes the mass number, while gamma decay changes neither, as it is pure energy. Now, let's complete these decay equations for iron-59, radium-224, and nitrogen-16. Pause the video and try to complete them yourself. Here is a question to consider. How could lead-202 decay into gold? You need to find a sequence of decays that balances the mass and atomic numbers. This can involve multiple alpha and beta decays. Finally, let's summarize the effects of different decays. When a nucleus emits an alpha particle, the atomic number falls by 2 and the mass number by 4. Beta particles are emitted by nuclei with too many neutrons. In beta decay, the atomic number increases by 1 while the mass number remains unchanged. Gamma rays consist of electromagnetic radiation that is emitted when the nucleus loses energy.